Good morning, I'm Kelsey Johnson. I'm a junior studying aerospace engineering and mechanics at the University of Alabama. This semester, I'm working with Dr. A.J. Agarwal in the Department of Mechanical Engineering on a project titled Passive Mitigation of Lean Direct Injection Combustion Systems in Aviation Gas Turbines. More specifically, this semester I've been working on the implementation of PIV data acquisition systems in the lean direct injection combustion strategy. As a byproduct of current aviation gas turbine engines, combustion processes, specifically the burning of fuel at very high temperatures, NOx is generated and dispelled into the environment. NOx generically stands for a group of compounds made of nitrogen and oxygen, and when these compounds reach the environment, they react to create ozone and particulate matter, or PM. Both of these are dangerous to human consumption as well as the environment, and because of this, a lot of federally funded organizations are concerned with reducing these emissions. As of 2012, the most recent standards were set for newly commissioned engines to include a 15% reduction in the emissions allowed since the previous standards set in 1996. Coupling these emissions standards with the ever-pressing need for increased fuel efficiency poses a great challenge for propulsion engineers. In general, to increase the fuel efficiency, it's expected to decrease the pressure and aspect ratios of the combustion engines, and because of this in part does us some favors in reducing the amount of soot and CO2 produced, but it also greatly increases the amount of NOx produced. So in order to have a combustion strategy that can increase fuel efficiency and also reduce the amount of NOx produced, we have found that the lean direct injection strategy has been efficient in doing so. In simple terms, the lean direct injection strategy takes advantage of greatly mixing the fuel and the air before it reaches the combustor, and in this way, leaner fuels can be burned quicker and cleaner. As you can see in the image here, this is a picture of the LDI setup we use in our laboratory. The Venturi and swirler are circled because these are the main proponents that allow us to have to achieve very high mixing. The Venturi has a decreased diameter, and this forces the mixing, as well as the swirler aids in this effort. The strategy, however, is susceptible to thermoacoustic instabilities, and these result due to noise, and this creates pressure oscillations as well as temperature oscillations within the combustor. In extreme cases, this can cause failure of the engine. And so we need a mechanism that can help us reduce these thermoacoustic instabilities. And as you can see here on the image on the left, this is an example of idealized flow structures that should occur within the combustor. You'll notice that there are two main regions that are of focus. There are the central and corner recirculation zones, and those will be important to our discussion next. So as I mentioned, the LDI system creates a lot of noise, and the sound waves that generate from these noise create pressure oscillations within the combustor. These oscillations will then in turn create a cyclic pattern of the amount of fuel that flows to the recirculation regions that I mentioned, and this fluctuation in fuel flow in turn creates a fluctuation in the heat release in these regions. In changing the amount of heat release, this obviously changes the amount of heat that's available for the combustion process. And so if we're able to reduce the amount of noise that the LDI setup creates, we can in turn help reduce some of these thermoacoustic instabilities. Additionally, the corner recirculation zones are of importance to us. In general, they're used to anchor the main flame, but if they become too large in the flow field, they can create more issues for us. And so we have aimed to find a mechanism to reduce the corner recirculation zones and even replace them in order to have a more reasonable way to anchor the main flame. And this is how we arrived on the porous insert. The porous insert achieves both of these goals in reducing thermoacoustic instabilities. It has been found to reduce noise, which we will discuss briefly, as well as it is effective in eliminating the corner recirculation zones. One of the greatest benefits of the porous insert is that the porous matrix allows some of the reactants to flow within it, and once they enter the matrix and then come to the top of the porous insert, they then combust there and form a small ring of flames, which we call flamelets. So here you can see a comparison of the flame fronts that we see in the LDI setup with and without an insert. If you look to the left, you'll see that there are the corner recirculation zones that we mentioned, and these do help stabilize the flame, but also you can see that this flame structure is less succinct and has some instabilities that you can actually visualize. If you look to the right, you'll see a case with a porous insert, and this demonstrates the small ring of flames we called flamelets, again, which are due to the fact that some of the fuel is allowed to pour into the matrix. And this helps stabilize the flame and create a much more succinct geometry. So because we are able to visualize that the porous insert does affect the flame front, we want to be able to quantitatively and qualitatively assess the differences that occur with and without a porous insert. We can achieve this through three main data acquisition techniques, the first of which is chemiluminescence. Chemiluminescence is a line of sight technique by which we can determine the occurrence of compounds called OH radical or OH star, and this is a group of particles that are associated with the breakdown of hydrocarbon fuels. So wherever we see these particles, we know that there is the breakdown of fuel and heat release, and therefore the flame structure. This sample piece of data here, you can see the no insert case versus the insert case, and you'll notice that the flame structures are extremely different. The dark red colors correlate to the highest intensities of OH radical particles, and so we take this type of data to determine how the insert visually, quantitatively, and qualitatively affects the flame front that we see. We also collect microphone data. As simple as this seems, microphone data can help us determine how effective the porous insert is in reducing the amount of noise that the LDI combustion system creates. And so as you can see in this sample piece of data, on the left there's the no insert case, on the right there's the porous insert case, and you can see that on average the porous insert creates much less noise, and this helps us understand the effects of the porous insert on reducing the pressure and temperature oscillations that result from sound. Lastly, and most importantly to the efforts of my project this semester, is PIV, or particle image velocimetry. PIV is the newest addition to our LDI test stand as of this semester, and so most of our efforts have been learning how to implement it and how we can best utilize it for our efforts. PIV is a non-intrusive way to determine the instantaneous flow field within the combustor. We achieve this with seed particles, which are made up of silicon compounds, and these are very small with nanometers of diameter, and we can track these particles over time. We use a laser sheet to illuminate these particles, and then we can use a very high-speed camera to take rapid pictures that can show us the position of the particles. So we take two very close images and can track a single particle from one frame to the next, and this can create a vector, and we can do this for the entire field of particles, creating a vector field. Then we can have thousands of these pairs of images and therefore vector fields, and we can create the instantaneous flow within the combustor over time. As I mentioned, this is the newest addition to our test stand, so the sample data I have here is very preliminary, and we have not really made any conclusions yet to the exact effect of the flow field, but certainly our future efforts will include determining how to best implement PIV, as well as collecting more of this data and preparing it for comparison. Additionally, in helping with the PIV system, I was allowed to pursue my own independent project in designing a seed catcher. As I mentioned, the seeds that we use for PIV are very small, and because of this, they're easy to inhale, as well as they're small enough to actually be absorbed into the skin. And so in great quantities, these can obviously be dangerous for consumption. And so part of my role this semester was to design a seed catcher that would make it safer and more convenient to implement PIV in our lab. I started in SOLIDWORKS, as you can see on the left. This is a picture of the seed catcher I designed. It's designed to slope to a single corner so that we can extract the particles pretty easily, and I was actually able to bring that into fruition this semester, and you can see that here. Lastly, as we move forward with this project, we want to implement even more new techniques. We would like to look at diffuse back illuminated imaging, or DBI, and this is essentially a technique where we can determine the occurrence of fuel spray within the combustor, and we would like to see how this affects the flame front that we see in LDI. And also we would like to move this testing to eventually to high pressure testing. Currently we only carry these tests out at atmospheric conditions, and so we would like to move forward in bringing that into a high pressure testing. So with that, I would like to take any questions.
Yeah, I was wondering if you could describe a little bit more about the DBI imaging technique that you're going to do in the future, and talk about how it could be implemented into your current test stands.
Sure. So DBI is a technique where we use essentially a very bright LED light, and we shine that into our test stand, and then in that way we can determine where the fuel occurs, because as some of the fuel spray will pass through the light, it will attenuate some of it, and then we can use a high-speed camera to capture that absence of light. And then we have some MATLAB code that essentially does a statistical analysis to determine the likelihood of fuel to exist in that region. And then hopefully we'll be able to use that to determine how the amount of fuel and where it occurs affects the flame front.
So about the porous inserts, I think it was slide 4. Is there any work that's going into further developing and optimizing the shape and porosity of these?
So our lab is not necessarily focused on optimizing this for specific applications, but we're basically performing very fundamental research on how it affects the flame front. And so there is a lot of room for developing the amount of pores that occur as well as the size of these pores, but we are leaving that up to industry companies who are interested in applying it to their specific engine to make that more tailored to what they would need.
Okay, thank you.
Choose the particular dimensions of the combustor that you mentioned with that, and what implications does that choice have upon your real-world applications?
So the combustor that we chose is not necessarily something that you would see exactly in the real world, but it is designed so that we can intensify the thermoacoustic instabilities we would see. And so in this way, we wanted to make that combustor, it has a 50 millimeter diameter. We made that specifically so that we could amplify those instabilities, and that way we could better study them.
Very good.